Hey everyone, welcome to this news story. Today, we look at the moon like never before, where humans are about to take their first permanent step beyond Earth. On its rocky surface, plans for the first moon base are moving faster than anyone expected. Scientists and engineers are designing habitats that can survive the cold nights, the harsh sun, and the deep craters that scar the ground. For decades, the moon has been a place of mystery and caution, but now technology and ambition are making it possible to live there for months at a time. How will humans build there? What challenges lie beneath the surface, in the dust, and under the low gravity? What secrets will this first base uncover about our closest neighbor in space? In this video, we travel to the moon's frontier to see what life might look like on our first true home beyond Earth, and explore what this new step teaches us about humanity's reach into the stars. The moon orbits the Earth at an average distance of approximately 384,400 kilometers. Its movement follows a slightly elliptical path, which causes small variations in distance over the course of its orbit. The lunar day, the time it takes for the moon to complete one rotation on its axis, matches the length of its orbit around the Earth, resulting in the same side always facing the planet. This synchronous rotation creates a near constant view of the far side of the moon from Earth, a surface that remained unseen until space probes were able to map it in the mid 20th century. The moon has a diameter of about 3,474 kilometers, roughly one-fourth that of Earth, and a mass of 7.35 times 10 to the 22nd kilograms. This smaller size gives it a gravitational pull that is one-sixth that of Earth's, a fact that significantly influences the behavior of objects and people on its surface. The surface of the moon is covered in a layer of fine, powdery material known as regolith. This layer is the result of billions of years of meteoroid impacts, which have broken down rock into small particles. The regolith varies in depth across different regions, ranging from a few meters in some highland areas to more than 10 meters in the darker Maria Plains. The composition of the regolith includes tiny fragments of rock, minerals such as plagioclase and pyroxene, and traces of metallic iron formed by micrometeorite impacts. This layer behaves differently from soil on Earth. It is dry, loose, and sharp-edged, and when disturbed, it can cling to surfaces and machinery due to electrostatic charges from solar radiation. The regolith's texture and distribution are key factors in designing habitats and equipment for future moon bases. The moon lacks a substantial atmosphere, which means there is no air to scatter sunlight, carry sound, or moderate temperature. Without atmospheric pressure, gases do not accumulate, and water cannot exist as a liquid on the surface. Solar radiation strikes the lunar surface directly, creating regions of extreme light and shadow. During the lunar day, the surface temperature can reach approximately 127 degrees Celsius, while during the lunar night, it can drop to nearly minus 173 degrees Celsius. These temperature extremes create stress on materials and structures, requiring careful engineering to maintain livable conditions inside habitats. Heat transfer occurs mainly through radiation and conduction, as there is no air to carry warmth or coolness across the surface. Lunar dust absorbs and radiates heat efficiently, which causes the ground to become very hot under sunlight and very cold when in shadow. Gravity on the moon influences both movement and the behavior of objects. At one-sixth Earth gravity, objects weigh less, making it easier to lift and move heavy items. Astronauts on previous missions experienced long, bounding steps due to the lower gravity, and materials like water, regolith, and building supplies will respond differently under these conditions. Liquids form spherical drops, and dust particles remain suspended longer when disturbed. The lower gravity also affects the human body over time, influencing muscle use, bone density, and cardiovascular function. For long term habitation, exercise and mechanical support will be necessary to maintain health and operational capability. The lack of a magnetic field leaves the moon exposed to the solar wind, which is a stream of charged particles emitted by the sun. These particles interact directly with the surface, gradually embedding in the regolith and producing chemical changes over millions of years. Solar storms can increase the flux of radiation, posing additional hazards for both equipment and people. Cosmic rays, which are high energy particles originating from outside the solar system, also reach the moon's surface without significant deflection. The combination of radiation exposure and the absence of atmospheric shielding is a primary concern for habitat design and human activity planning. Light on the moon behaves differently than on Earth. The angle of sunlight creates stark contrast between illuminated and shadowed regions. At the terminator, the line between day and night, shadows are elongated and deep, revealing subtle features in the surface topography. In shadowed craters, temperatures remain near the minimum for extended periods, allowing for the preservation of water ice in permanently shadowed regions. Sunlight at the poles is nearly continuous during the lunar summer, while at other times it can be absent for weeks or months. These variations in light availability influence decisions about solar power generation and base placement. The moon's surface is marked by impact craters, formed over billions of years by collisions with meteoroids of various sizes. Some craters are shallow, a few meters across, while others are massive basins, hundreds of kilometers wide. Ejecta from these impacts spreads over the surrounding terrain, forming secondary craters and layers of fragmented rock. The distribution and density of craters are important for navigation, habitat placement, and construction planning. Crater walls can cast long shadows, affect local temperatures, and present challenges for mobility and equipment operation. The uneven surface requires careful mapping and engineering for any construction projects, including landing pads, roads, or habitat foundations. Highland regions of the moon are composed of older, more reflective material than the Maria Plains. The highlands are heavily cratered and rugged, while the Maria are relatively smooth and dark, formed by ancient volcanic lava flows. The contrast between these regions provides both challenges and opportunities for exploration. While the highlands may be difficult to traverse, they contain materials rich in aluminum, calcium, and other minerals useful for building and manufacturing. The Maria, with flatter terrain, can offer more straightforward landing sites and areas suitable for base expansion. Understanding the geology of both regions is essential for long-term planning of a moon base. Seismic activity on the moon is minimal compared to Earth, but not absent. Moonquakes occur, often caused by tidal forces exerted by Earth's gravity or by the settling of cooled lunar rock. These quakes are generally weak, but their frequency and location must be considered when designing structures. Foundations need to accommodate minor shifts, and habitats must resist potential stress from ground movement. The moon's interior, while less active than Earth's, still contains heat from radioactive decay and residual formation energy. This heat influences the subsurface temperature, which can be useful in planning underground habitats or resource extraction. The moon's low density and lack of atmosphere create a unique visual environment. The sky appears black at all times, even during daylight, because there is no atmosphere to scatter sunlight. Stars are visible above the bright surface, and the Earth itself appears larger and more colorful than the moon does from its surface. Shadows are sharp, with no gradual transition, and reflective surfaces can produce glare that affects visibility. Dust kicked up by human activity or machinery remains suspended for longer periods, subtly altering the appearance of the surface near bases or landing sites. Observing these visual conditions is important for navigation, monitoring, and planning construction or research operations on the moon. The combination of low gravity, extreme temperature swings, exposure to radiation, and fine dust makes the moon a challenging environment for human activity. Every aspect of movement, construction, and life support must consider these factors. Structures must provide thermal insulation, radiation shielding, and stable foundations. Mobility systems must handle loose regolith and irregular terrain. Energy systems must rely on predictable solar patterns or stored reserves. Water and air must be produced or recycled within the base, as external supplies are limited. Each of these considerations defines the framework for planning the first moon base and shapes the approach to long term habitation and exploration. The surface of the moon is divided into two main types of terrain, known as the Maria and the highlands. The Maria are the darker regions, relatively smooth and low lying, formed by ancient volcanic lava flows. These plains cover approximately 16% of the lunar surface and are found primarily on the near side. The lava that formed the Maria filled large impact basins billions of years ago, creating broad, flat areas with fewer craters than the older highlands. The smoothness of these regions makes them favorable for landings and construction, although the surface is still covered in a layer of fine regolith that varies in depth from a few meters to more than 10 meters in some locations. Beneath the regolith, solid basalt rock forms the foundation of the plains, providing a stable base for potential structures and research installations. The highlands are brighter and more heavily cratered than the Maria. These areas are older, consisting of mountains, ridges, and rugged terrain that rise above the surrounding plains. The highlands are composed mainly of anorthosite, a rock rich in plagioclase feldspar, which reflects more sunlight and gives the regions a pale appearance. The density of craters is much higher in the highlands due to their greater age. Impacts over billions of years have created overlapping craters, steep walls, and fragmented rock layers. The combination of rough terrain and deep cratered surfaces presents challenges for mobility and construction, but it also provides insight into the moon's geological history and the processes that shaped its surface. Impact craters are a dominant feature on the lunar surface. They vary greatly in size, from tiny pits a few meters across to basins hundreds of kilometers in diameter. Each crater has a raised rim, an interior floor, and sometimes central peaks formed by the rebound of the crust immediately after impact. Material excavated during impacts is ejected across the surrounding landscape, forming secondary craters and deposits of fractured rock. The frequency and distribution of craters are indicators of the moon's age and the intensity of meteoroid bombardment. Studying crater patterns helps determine safe zones for construction and identifies areas where the regolith may be thick enough to provide natural shielding for habitats. Volcanic activity in the moon's past also shaped its surface. Lava erupted through fissures in the crust, filling basins and creating the smooth plains of the Maria. The composition of these lavas is primarily basalt, a dense and iron-rich rock that solidifies to form solid layers capable of supporting heavy structures. Small volcanic domes and rills, which are narrow channels formed by past lava flow, remain visible in some regions. These features reveal the internal heat and geologic processes that were once active and suggest areas where the subsurface rock may be more uniform and stable. Understanding the distribution and thickness of lava flows is important for selecting construction sites and planning excavation for subsurface habitats. Tectonic activity on the moon is minimal but not entirely absent. Wrinkle ridges, faults, and grabens indicate slow movement and contraction of the crust over time. These features are most common in the Maria and suggest that the cooling of lava and crust created stress that caused the surface to deform. Fault lines are generally small compared to those on Earth, and the tectonic activity today is largely dormant. Nevertheless, mapping these structures is important for understanding subsurface stability and ensuring that habitats are built in areas unlikely to experience ground shifts or cracking. The polar regions of the moon contain unique geological features. Craters near the poles often have areas that remain in permanent shadow, as sunlight never reaches the deepest parts of these depressions. These permanently shadowed regions are extremely cold, maintaining temperatures well below minus 170 degrees Celsius. Scientists have discovered water ice trapped within these craters, preserved over billions of years. The presence of ice is critical for the potential sustainability of a moon base, as it can be used to produce water, oxygen, and hydrogen. Terrain mapping shows that the poles also contain elevated regions that receive nearly continuous sunlight during the lunar summer. These sunlit peaks provide opportunities for solar energy collection and are considered prime locations for the placement of habitats and energy infrastructure. Mineral composition varies across the lunar surface, influencing both construction and resource utilization. The highlands are rich in plagioclase feldspar, while the Maria contain higher concentrations of iron and magnesium. Titanium is also present in certain basalt flows, particularly in the Maria near the Oceanus Procellarum. Small deposits of ilmenite, a titanium iron oxide, have been identified as a potential source of oxygen through chemical processing. The distribution of these minerals guides decisions for site selection, construction material sourcing, and in situ resource utilization. By processing regolith locally, it may be possible to produce building materials, such as concrete, shielding layers, or protective coatings without transporting heavy supplies from Earth. Crater floors and the interiors of rilles provide additional insight into subsurface materials. Layers of solid rock lie beneath the regolith, and in some locations, the crust is fractured or tilted due to past impacts or thermal stress. Excavation of these areas could reveal more stable rock formations suitable for habitat foundations or underground laboratories. The moon's regolith also contains small amounts of volatile compounds, such as hydrogen and helium 3, which are embedded in the surface by the solar wind. These compounds are being studied for potential energy use, with helium 3 considered as a fuel for future fusion energy experiments. The combination of minerals, volatiles, and stable rock layers makes detailed geological surveys essential before construction begins. The slopes of craters and hills influence the behavior of loose regolith. Material on steep inclines can move under its own weight, especially when disturbed by human activity or machinery. Dust particles may become airborne and settle over time, altering the surface profile. Understanding these processes allows engineers to predict areas of potential regolith movement and plan stabilization measures for roads, landing pads, or habitat platforms. Terrain modeling combines satellite imagery, laser altimetry, and surface measurements to create accurate three-dimensional maps for construction planning. Regolith thickness and compaction vary between Maria and highlands, and even within individual craters. Thin regolith over solid basalt or anorthosite may provide a strong foundation for structures, while thick, loose layers could require reinforcement. Laboratory experiments using lunar simulants on Earth help predict how real regolith will respond to load, vibration, and mechanical wear. Equipment for excavation, construction, and mobility must account for these differences, as well as the abrasive nature of lunar dust. Testing vehicles and tools in simulated environments ensures they can operate safely on slopes, uneven terrain, and loose material. The moon's surface also preserves a record of its geological past. Crater chains, overlapping impact basins, volcanic domes, and tectonic ridges form a layered history that spans more than 4 billion years. Each feature provides clues about the processes that shaped the moon and the distribution of materials near the surface. By studying these formations, scientists can select sites that offer both stability and access to valuable resources. Detailed geological maps are essential for planning habitat locations, power systems, and excavation operations. The interplay between impact craters, volcanic flows, and tectonic features defines the complexity of the lunar surface. Large basins filled with basalt are surrounded by highland ridges, while smaller craters punctuate both smooth and rugged regions. This varied terrain requires careful consideration for landing, construction, and long term habitation. Site selection balances flat, stable areas for infrastructure with access to resources such as ice, regolith for building, and minerals for in situ processing. Scientific understanding of this complexity is critical for ensuring that the first moon base is constructed on the safest and most resource rich locations available. The moon's geology continues to influence modern exploration plans. Data from orbiters, landers, and rovers have mapped surface composition, topography, and regolith characteristics. High resolution images allow planners to identify hazards, determine optimal landing sites, and locate regions where habitats, solar arrays, and excavation sites can coexist. By integrating geological knowledge with engineering design, it is possible to plan for the challenges of the moon's surface while taking advantage of its mineral wealth, stable rock formations, and ice deposits. The combination of maria, highlands, craters, volcanic structures, and polar features creates a diverse environment. Each region presents opportunities and challenges for the first moon base. Understanding surface composition and geological structure is essential for construction, mobility, and long term sustainability. Decisions about habitat placement, excavation, and resource use are all guided by careful observation and measurement of these features. The moon's surface is both a record of its history and a foundation for future human activity, shaping how a base can be designed and how life support systems will operate in the long term. The moon experiences extreme temperature changes due to its slow rotation and lack of atmosphere. A full lunar day lasts approximately 29.5 Earth days, meaning that sunlight can fall on the same surface for about 14 Earth days, followed by roughly 14 days of darkness. During the daytime, temperatures can rise to approximately 127 degrees Celsius. Sunlight strikes the surface directly, and without an atmosphere to scatter heat or diffuse light, the ground absorbs energy rapidly. Rocks and regolith become hot to the touch, and surfaces facing the sun emit infrared radiation. Shadows offer little relief, as heat transfers primarily through direct contact and radiation rather than air movements. During the lunar night, temperatures fall drastically, reaching nearly minus 173 degrees Celsius in unexposed regions. The absence of air prevents heat retention, causing surfaces to lose energy quickly. Regolith, which can store heat for a short period, cools rapidly once sunlight disappears. Rocks retain warmth slightly longer, but even large boulders eventually reach the frigid temperatures of their surroundings. Thermal expansion and contraction occur in response to these changes, which can cause cracking and mechanical stress in both natural rock formations and human made structures. Habitats and equipment must be designed to tolerate repeated cycles of heating and cooling without structural failure. The soil on the moon behaves uniquely under temperature extremes. Lunar regolith is fine and powdery, but it contains small fragments of rock and glass created by meteoroid impacts. During the day, sunlight heats the top layer of regolith, while layers beneath remain cooler. Thermal conduction is slow, so only the upper centimeters reach maximum daytime temperatures. During the night, the surface rapidly loses heat, creating a strong gradient between warm and cold layers. Understanding this gradient is essential for designing foundations, insulation, and underground habitats. Heat storage strategies can take advantage of the slower cooling of subsurface layers to moderate internal temperatures. Rocks on the moon also exhibit thermal behavior influenced by their composition and color. Dark basalt rocks found in the Maria absorb more sunlight and heat more quickly, while lighter anorthosite of the highlands reflects more light and heats less. As temperatures rise, thermal expansion can lead to stress fractures, especially along existing cracks or boundaries between rock types. These processes contribute to the slow breakdown of surface materials over time and affect the stability of areas intended for construction or landing. Engineers must consider these variations when selecting sites for solar panels, landing pads, and habitat foundations. The lack of a magnetic field on the moon exposes the surface to solar radiation and cosmic rays. High energy particles from the sun, known as the solar wind, strike the surface directly. Cosmic rays originating from beyond the solar system also reach the moon unimpeded. Both forms of radiation interact with regolith and rocks, slowly altering their chemical structure over millions of years. For human habitation, exposure to this radiation is a major concern. Protective measures, including shielding, underground construction, and specially designed materials, are required to reduce risks associated with long term occupancy. Solar radiation includes ultraviolet, visible, and infrared light. Ultraviolet radiation is particularly energetic and can break molecular bonds in exposed surfaces. Over long periods, this contributes to the formation of a fine layer of chemically altered regolith. Infrared radiation contributes to heating the surface, while visible light provides energy for solar panels. Both direct and reflected sunlight must be considered when designing energy systems and planning the placement of habitats. Proper orientation and shielding can optimize energy collection while minimizing exposure to harmful rays. Cosmic rays are less frequent than solar radiation but carry higher energy. They penetrate materials more deeply, requiring thicker shielding for protection. Regolith itself provides partial shielding. Even a meter of compacted soil can reduce exposure significantly. Excavated material can be repurposed to create protective berms or layers over habitats. Understanding the intensity, frequency, and directionality of cosmic rays helps engineers design structures that protect inhabitants and sensitive equipment without excessive use of imported materials. Temperature swings also affect mechanical systems. Metal components expand and contract differently than rock or regolith, which can lead to loosening joints, cracks, or deformation in tools, vehicles, and structures. Electrical systems must tolerate wide thermal ranges, and lubricants must remain functional under extreme heat and cold. Surface operations require careful planning to prevent equipment failure, as the moon offers no natural environmental buffering. Vehicles, robots, and machinery must be tested for performance under these conditions to ensure reliability over extended periods. Shadows, especially near crater walls, experience lower temperatures than open plains. Permanently shadowed craters near the poles can maintain extreme cold for billions of years. Ice deposits found in these regions are preserved precisely because temperatures remain below freezing. The contrast between sunlit slopes and shadowed areas is sharp, creating local microenvironments with distinct thermal properties. Thermal modeling of these areas informs site selection for habitats, resource extraction, and energy collection. Even small, differences in sunlight exposure can influence structural design and operational planning. Thermal energy management is central to the first moon base. During the day, habitats must shed excess heat to maintain livable internal temperatures. At night, insulation and stored heat prevent freezing. Underground construction takes advantage of the relative stability of subsurface temperatures, which vary less than the surface. Layered regolith and rock can act as natural insulation and radiation shielding. Heat pumps, radiators, and thermal storage systems can moderate temperature extremes, allowing internal systems to operate efficiently despite the harsh lunar environment. Regolith's thermal properties also affect mobility. Vehicles driving across sunlit areas may experience hotter surfaces while shaded areas remain cold. Differential heating can cause expansion in tires, wheels, or tracks. Dust kicked up by movement behaves differently depending on temperature. As warmer, particles may become more prone to sticking, while colder dust remains brittle and sharp. These factors influence both the design of transport vehicles and the methods used to prepare landing sites, roads, and work areas. The daily temperature cycle drives other environmental effects. Thermal gradients can cause regolith particles to move, crack rocks, and shift loose material. Over time, this contributes to a dynamic surface, with fresh debris covering older layers and exposing new materials. Habitats and equipment must accommodate these ongoing changes, accounting for both gradual surface evolution and sudden thermal stress events. Planning must incorporate long term monitoring and maintenance strategies. Radiation also affects electronics and materials. Prolonged exposure can degrade semiconductors, plastics, and coatings. Shielding strategies include layered metals, regolith coverings, and specialized materials that block or absorb high energy particles. Solar storms pose temporary but intense increases in radiation levels, which can last hours to days. Predicting and monitoring these events is critical to ensure the safety of equipment and personnel. Data from previous missions provide patterns of solar activity and cosmic ray intensity, informing protective measures for long term habitation. Thermal and radiation considerations together define the environmental envelope for human activity. Habitats must maintain stable internal temperatures, protect against extreme cold and heat, and block radiation. Mobility and mechanical systems must function reliably across the full temperature range. Material selection and construction techniques must consider thermal expansion, contraction, and degradation from radiation exposure. All of these factors influence design, operational planning, and the longevity of structures on the lunar surface. Temperature and radiation are interdependent in their effects. For example, surfaces exposed to sunlight for long periods accumulate thermal energy, but also absorb higher doses of radiation. Conversely, shadowed areas remain cold, but can trap radiation induced chemical changes in regolith and ice deposits. By mapping both thermal cycles and radiation intensity across potential base locations, planners can select sites that balance energy collection, resource access, and protective conditions. The combination of extreme heat, cold, and radiation creates a challenging environment for any human activity. Equipment and habitats must withstand these forces without the benefit of Earth's atmosphere. Thermal control systems, insulation, and radiation shielding become as critical as structural integrity. Long term planning incorporates these factors into every aspect of a moon base, from placement of solar panels to excavation of underground laboratories. A deep understanding of temperature and radiation patterns is essential to ensure that infrastructure can operate safely and effectively in this environment. Thermal behavior also impacts energy storage and generation. Solar panels operate most efficiently when temperatures are within moderate ranges. Excess heat can reduce efficiency, while extreme cold can damage components or slow chemical reactions in batteries. Storage systems must hold energy collected during long daytime periods for use during the extended night. By considering thermal and radiation constraints together, engineers can design reliable power systems that support habitats, mobility, and research activities. Finally, temperature extremes and radiation influence human safety and operations. Protective suits must resist heat and cold while allowing mobility. Shields, habitat walls, and underground shelters mitigate radiation exposure. Understanding these environmental limits shapes every decision about timing, location, and methods for surface work. By integrating knowledge of thermal cycles, radiation patterns, and material behavior, planners can create a sustainable environment for long term human presence on the moon. Human presence on the moon introduces challenges that are distinct from those on Earth. The lower gravity, about 1/6 of Earth's, affects the way bodies move, objects behave, and materials interact. When walking, humans must adjust to reduced weight, which alters balance and muscle use. Simple tasks like lifting, pushing, or carrying equipment feel different, as objects weigh less but retain the same mass. This reduced gravitational pull also affects liquids, causing them to form spheres more readily and altering the flow of water, fuel, or other fluids. Handling and transferring materials require careful control to prevent spillage or uncontrolled motion. Muscles and bones respond slowly to low gravity. Without regular exercise, muscle mass decreases and bone density declines over time. Cardiovascular function also adapts, with changes in blood distribution and heart activity. Maintaining physical health requires equipment designed to simulate resistance or weight bearing activity. Exercise machines, such as treadmills with harnesses or resistance devices, are planned for habitats to counteract the effects of long duration exposure to low gravity. Any habitat must provide space and equipment for these routines, as maintaining human physiology is critical to operational effectiveness. The behavior of dust on the moon presents another challenge. Lunar dust is fine, sharp, and abrasive, created over billions of years by meteoroid impacts. Unlike Earth soil, it lacks moisture and has jagged edges, allowing particles to cling to surfaces, clothing, and equipment. Dust can infiltrate seals, joints, and moving parts, causing wear and damage over time. Mechanical abrasion occurs as particles grind against metal, glass, and composites, potentially reducing the lifespan of tools, vehicles, and habitat components. Dust management is an essential part of planning for human activity and base maintenance. Electrostatic charging of lunar dust further complicates handling. Particles exposed to sunlight can carry an electric charge, causing them to adhere to surfaces or become airborne when disturbed. Activities such as walking, driving vehicles, or moving equipment release clouds of dust that can settle on solar panels, sensors, or habitat exteriors. Preventing accumulation requires cleaning systems, dust resistant coatings, and controlled airlocks. Even small amounts of dust in critical systems can affect performance, so ongoing monitoring and maintenance are required. Radiation exposure on the moon is significant because there is no atmosphere or magnetic field to shield the surface. High energy solar particles and cosmic rays can penetrate deep into the skin and materials, posing health risks for humans and degrading equipment. Shielding for habitats includes layers of regolith, metals, or specialized polymers to reduce exposure. Underground, construction provides natural protection, as even a meter of rock or soil absorbs much of the harmful radiation. Habitat placement and orientation are planned to minimize direct exposure, while operational protocols account for solar storms or periods of increased activity. Life support systems are a central concern for human survival. The moon has no breathable air, so habitats must provide oxygen and remove carbon dioxide continuously. Water must be produced, recycled, or delivered from Earth, while humidity, pressure, and temperature are carefully controlled. Air circulation systems prevent the buildup of harmful gases and dust, and filtration systems remove fine particles. Redundant systems ensure continuous operation, as failure could be life-threatening. Integration of air, water, and waste management systems allows long-duration habitation without dependence on frequent resupply. Thermal regulation is critical for both comfort and safety. Habitats must maintain stable temperatures despite external swings from plus 127 degrees Celsius to minus 173 degrees Celsius. Insulation, radiators, and thermal storage systems help manage heat gain and loss. Subsurface habitats benefit from the relative stability of underground temperatures, reducing the need for extensive energy input. Structures above the surface must account for rapid heating and cooling cycles, which can stress materials, joints, and equipment. Energy efficient designs optimize power usage, while ensuring human occupied spaces remain within safe temperature ranges. Energy supply on the moon relies primarily on solar power. Continuous sunlight is available at some polar sites during the lunar summer, while other locations experience extended periods of darkness. Solar panels must be positioned to maximize collection, and energy storage systems, such as batteries or regenerative fuel cells, store power for nighttime use. Managing energy involves balancing production, storage, and demand, particularly for life support, thermal control, and mobility systems. Reliability is essential, as a failure of the power system could compromise both habitat integrity and human safety. Material handling in low gravity requires special procedures. Large, heavy components can be moved more easily than on Earth, but their inertia remains unchanged. Sudden movements can create uncontrolled motion, requiring careful anchoring and restraint systems. Construction tasks must account for both weight reduction and the tendency of materials to float or drift if not properly secured. Ropes, clamps, and tethers are commonly planned to stabilize objects during assembly, excavation, or repair activities. Even simple operations require attention to the combined effects of low gravity, loose regolith, and dust. Mobility for humans and machines is affected by the moon's terrain and gravity. Walking or driving across loose regolith can cause slipping, sinking, or dust clouds that reduce visibility. Wheels, tracks, or legs must distribute weight to avoid sinking, while dust mitigation prevents abrasion and system damage. Suits and vehicles are designed to allow flexibility and movement while providing protection from temperature extremes, radiation, and mechanical hazards. Planning routes, landing areas, and construction zones involves mapping slopes, regolith depths, and rock distribution to minimize risk and facilitate efficient operations. Radiation, dust, and gravity together influence long term planning. Habitats, vehicles, and tools must resist abrasion, thermal stress, and particle infiltration while maintaining human safety. Redundant systems, protective measures, and constant monitoring are necessary to ensure operational continuity. Even small lapses in maintenance or design can have compounding effects, so engineering strategies integrate multiple layers of defense, including physical shielding, dust-resistant materials, and energy reserves. And psychological and physical well-being depends on reliable life support, mobility, and energy systems. Although humans will adapt physiologically to low gravity, protective measures against radiation and dust remain critical. Temperature control ensures habitats remain habitable, while solar and energy storage systems support continuous life support operations. Maintenance protocols, monitoring, and careful operational procedures reduce risk and allow extended missions on the lunar surface. Construction of habitats requires careful attention to these challenges. Building with local regolith, using prefabricated modules, or excavating subsurface structures all involve managing low gravity, dust, and thermal extremes. Tools must be designed to function under abrasive conditions, and assembly methods account for the unique mechanical and environmental factors. Integration of energy systems, radiation shielding, and thermal control ensures that human presence can be sustained safely and efficiently. Overall, the combination of low gravity, abrasive dust, high radiation, and extreme temperatures defines the constraints for human activity on the moon. Every aspect of mobility, construction, and daily operations is affected by these environmental conditions. By studying these challenges and developing engineering solutions, planners can design habitats, vehicles, and systems that allow humans to live and work on the moon for extended periods. Success depends on a careful balance of physiology, material science, and environmental adaptation, with each factor influencing how a moon base can be established and maintained. Human understanding of the moon has grown steadily since the first observations through telescopes. The Apollo missions marked the first time humans landed and walked on the lunar surface. Between 1969 and 1972, 6 missions successfully placed astronauts on the moon. Each mission deployed equipment, collected samples, and conducted experiments that provided a foundational understanding of the lunar environment. The astronauts studied surface geology, examined rocks, and measured radiation levels. The missions demonstrated the feasibility of human activity on the moon and provided the first direct evidence of the challenges of living and working in a low gravity, airless environment. Apollo astronauts collected more than 380 kilograms of rock and soil samples. These samples came from Maria, highlands, and crater regions. Analysis revealed differences in composition between younger basalt flows and older anorthosite formations. Rocks showed evidence of ancient volcanic activity, impact processes in the accumulation of solar wind particles. Soil studies demonstrated the sharp, abrasive nature of regolith and its tendency to cling to surfaces. These findings were critical for understanding how the surface would interact with tools, vehicles, and habitats, informing future design considerations for lunar bases. Robotic missions have complemented human exploration. Landers and rovers, including those from the Soviet Lunar Program, China's Chang'e missions, and multiple orbiters from the United States, have provided continuous observation and mapping of the moon. Instruments on these missions measure topography, mineral composition, temperature, radiation, and magnetic properties. Rovers traverse the surface, sending detailed images and data back to Earth. These observations cover areas beyond the reach of human missions and provide high resolution maps for future site selection. Satellite mapping has transformed understanding of the moon. Laser altimetry measures surface height, allowing for precise mapping of craters, ridges, and plains. Multispectral imaging identifies variations in mineral composition, distinguishing Maria, highlands, and volcanic features. Thermal imaging tracks surface temperature variations over day-night cycles, while gamma and neutron detectors measure elemental composition from orbit. These maps provide critical information for choosing landing sites, locating resources, and designing bases that can withstand environmental extremes. Data from lunar missions also measure radiation exposure and energetic particle flux. Instruments on orbiters and landers have recorded the intensity of solar wind, cosmic rays, and solar storms. Measurements show that radiation varies with location, altitude, and solar activity. These datasets inform the design of habitats, spacesuits, and equipment, ensuring adequate shielding and operational planning. Continuous observation allows for predictive models that anticipate periods of higher radiation and guide safe scheduling of surface activities. Lunar exploration missions have provided insight into dust behavior. Observations from Apollo missions revealed that dust adheres to suits, equipment, and instruments. Robotic landers confirm that dust can interfere with moving parts and reduce the efficiency of solar panels. The shape, size, and electrostatic properties of lunar dust are well documented, giving engineers data to design cleaning systems, dust resistant materials, and operational procedures to reduce hazards. This information remains critical for planning long term habitation. The moon has been mapped in increasing detail over decades. Global mapping identifies potential base locations based on terrain, sunlight exposure, and resource availability. Data reveals slopes, regolith depth, crater density, and surface composition. Areas near the poles are mapped for permanently shadowed regions, as where ice may be preserved. Sunlit peaks are identified for solar energy collection. These high-resolution maps guide decisions for habitat placement, power systems, and mobility pathways. Geological studies conducted by Apollo missions and robotic landers revealed the history of lunar formation. Rocks indicate that the moon formed from a molten state, with volcanic activity shaping its Early surface. Impacts created basins and craters that dominate today's terrain. By studying these features, scientists understand regolith distribution, rock stability, and subsurface conditions. Knowledge of past activity informs engineering decisions for excavation, construction, and resource use, as well as hazard mitigation for future missions. Radiation measurements and environmental monitoring during past missions provide lessons for human habitation. Apollo astronauts experienced short duration stays and relied on spacecraft for shielding. Instruments left on the surface record data over decades, demonstrating the cumulative effect of solar and cosmic radiation. This information allows planners to model long term exposure for habitats and mobility systems, ensuring that protection is adequate for extended missions. Subsurface habitats are a direct response to these findings, using natural shielding to reduce radiation risk. Mobility and equipment design have benefited from historical data. Lunar rovers used during Apollo missions showed how wheels interact with regolith, how slopes affect traction, and how dust interferes with mechanical components. Robotic landers confirm these behaviors over larger regions that's in varying terrain. These studies inform the design of future transport systems, excavation equipment, and construction machinery. Vehicles and tools must balance stability, durability, and the ability to operate across both smooth plains and rugged highlands. Lessons from human and robotic missions demonstrate the importance of redundancy. Critical systems for life support, energy, and communication must have backup systems. Apollo missions used multiple redundancies to ensure astronaut safety, and robotic missions use redundancy to maintain continuous data collection despite failures. Designing a moon base applies the same principles. Every essential function, from oxygen production to thermal regulation, requires secondary systems or alternative methods to prevent mission failure. Experience from past missions also informs planning for logistics. Landers and rovers show that cargo must be carefully secured, that dust can damage exposed materials, and that temperature extremes affect both electronics and structural components. Timing of operations, sequencing of tasks, and placement of habitats and equipment are all guided by empirical data. By combining insights from multiple missions, planners can design work procedures that maximize efficiency and minimize risk. Ongoing observation continues to refine knowledge of the moon. Orbiters provide updated imagery, monitor surface changes, and track environmental factors. Missions like the Lunar Reconnaissance Orbiter map terrain at sub-meter resolution, measure surface temperature variations, and identify potential hazards. Continuous data collection ensures that planning for the first moon base is based on the most accurate and up-to-date information. This approach reduces uncertainty and allows for more precise engineering and operational decisions. Scientific instruments deployed during historical missions remain functional for decades, recording temperature, seismic activity, and radiation levels. These long-term data sets provide insight into the moon's dynamic environment, including micrometeorite impacts, regolith movement, and subtle ground shifts. Such measurements guide the design of foundations, protective structures, and operational schedules, ensuring that habitats are placed in locations that minimize risk from natural environmental changes. Understanding the moon's surface and environment through exploration has allowed engineers and scientists to plan for sustainable human activity. Knowledge of terrain, material properties, radiation, and dust behavior directly influences the design of habitats, mobility systems, and life support. By combining historical experience with ongoing observations, planners can anticipate challenges and develop solutions that support long duration missions and eventual permanent presence. Exploration missions have also provided insight into energy management. Solar power collection, battery storage, and thermal control are informed by temperature cycles and sunlight availability measured across multiple lunar days. These data guide the placement of solar arrays, energy storage facilities, and habitats to ensure consistent power supply. Understanding environmental patterns allows planners to optimize energy use, reduce risk, and ensure the continuous operation of life support and construction systems. Overall, historical and ongoing lunar exploration has created a comprehensive understanding of the moon's environment. Apollo missions provided direct human observation, sample collection, and short term operation data. Robotic landers and orbiters expanded coverage, measured physical and chemical properties, and monitored radiation and temperature. Together, these missions form the basis for planning the first moon base, providing empirical knowledge essential for safe construction, long term habitation, and operational sustainability. Designing a moon base begins with consideration of habitat types suitable for the environment. Inflatable habitats offer flexibility and rapid deployment. These structures are constructed from strong, layered fabrics that can be packed into a small volume for transport and then expanded on the surface. Once inflated, the interior provides livable space while maintaining pressure and supporting life systems. Inflatable habitats are typically reinforced with external shielding or covered with layers of regolith to protect against radiation and micrometeorites. They provide a practical solution for initial surface operations while permanent structures are being developed. Modular habitats are another approach. Prefabricated sections are designed on Earth and assembled on the Moon. Each module can serve a specific function, such as living quarters, laboratories, storage, or power management. Modules can be connected to form larger complexes as additional units arrive. This approach allows flexibility in layout and expansion, and the modules are built to withstand pressure differences, temperature swings, and mechanical stress. Structural components are designed for low gravity, with joints and fasteners that accommodate both movement and thermal expansion. Modules often include internal life support and air circulation systems, with interfaces that allow integration into larger networks. Underground habitats utilize the moon's regolith and rock for natural protection. Excavating beneath the surface provides shielding from radiation, micrometeorite impacts, and temperature extremes. Subsurface structures are designed with reinforced walls, arches, or domes, using rock or concrete derived from lunar materials. Tunnels and chambers are interconnected to form larger living and working spaces. Access points are limited and controlled through airlocks, and ventilation systems circulate air while maintaining pressure. Subsurface construction reduces the need for heavy imported shielding, making it an efficient solution for long duration habitation. Material selection is critical for any moon base. Metals, such as aluminum and titanium alloys, are commonly used for structural components due to their strength to weight ratios and resistance to corrosion. Composites offer similar advantages, with added flexibility for curved or irregular shapes. Lunar regolith can be processed to create concrete like materials, providing additional building options. Techniques such as sintering, where regolith is heated to form solid blocks, or additive manufacturing, which 3D prints structures from lunar soil, allow in situ resource utilization. This reduces the mass that must be launched from Earth and provides shielding for radiation and temperature extremes. Airlocks are essential for connecting habitats to the lunar surface. They must maintain pressure, prevent contamination by dust, and allow safe movement of personnel and equipment. Airlock designs often include two doors, a pressure chamber, and systems to circulate air and remove dust. The chamber may also serve as a storage or decontamination area, ensuring that lunar dust does not enter living spaces. Life support systems are integrated with airlocks to maintain oxygen levels, remove carbon dioxide, and regulate humidity during ingress and egress. Proper design prevents loss of air pressure and protects both inhabitants and equipment. Life support systems maintain a breathable atmosphere, temperature control, and water recycling. Oxygen can be generated from stored supplies or extracted from lunar regolith. Carbon dioxide is removed using chemical scrubbers or recycling systems. Water is purified and recycled through closed loop systems, ensuring that supply remains constant. Humidity, pressure, and temperature are controlled to simulate Earth like conditions. Redundancy is built into these systems to ensure continuous operation, with backup units or alternative methods ready in case of failure. Integration with the habitat's structure allows systems to operate efficiently and minimize space and weight. Radiation shielding is a primary consideration for habitat design. Layers of regolith, water, or specialized materials, such as polyethylene, are used to absorb high energy particles. Habitats may be partially buried or surrounded by berms of soil. Materials with high hydrogen content are particularly effective at blocking cosmic rays. Shielding strategies are tailored to the location, with polar bases benefiting from natural terrain that reduces exposure, while equatorial sites may require additional coverage. Reducing radiation exposure is essential to ensure the health of inhabitants over long duration missions. Thermal insulation strategies are integrated into habitat design to maintain stable internal temperatures. Multi layer insulation, reflective coatings, and thermal blankets reduce heat transfer. Subsurface habitats benefit from the natural insulating properties of rock and regolith. Surface habitats incorporate radiators and heat exchangers to dissipate excess energy during the long lunar day. At night, stored heat can be used to maintain livable conditions. Thermal control systems operate in concert with energy supply and life support systems to provide a stable environment for occupants. Structural considerations account for both pressure and external loads. Low gravity reduces the weight of structures, but does not eliminate stress from pressurization, thermal expansion, or micrometeorite impacts. Domes, arches, and reinforced walls distribute loads efficiently. Connections between modules must accommodate slight movements without compromising integrity. Materials are tested for performance under repeated heating and cooling cycles, exposure to radiation, and abrasion from dust. Understanding these factors ensures long term reliability of both temporary and permanent habitats. Integration of habitat systems involves careful planning. Life support, power, thermal regulation, communications, and mobility systems are designed to function together. Modules are connected with utility lines, ventilation ducts, and structural supports. Power systems, often based on solar arrays and batteries, supply energy for lighting, heating, and equipment operation. Redundant pathways for power, air, and data reduce the risk of single point failures. The combination of careful material selection, shielding, insulation, and system integration creates a livable environment on the moon while minimizing dependency on Earth. Construction methods vary depending on habitat type. Inflatable modules require minimal assembly, but rely on external protection from Rexley thither shields. Modular units are assembled using cranes, robotic manipulators, or human crews. Subsurface habitats may involve excavation using mechanical diggers, sintering equipment, or robotic 3D printing systems. Each method considers the challenges of low gravity, dust, temperature extremes, and mechanical stress. Planning the sequence of construction tasks ensures stability and safety throughout the building process. Access and mobility within the base are considered in design. Corridors, as airlocks and internal pathways, are arranged to allow easy movement between modules and work areas. Surface access points as accommodate vehicles, scientific equipment, and transport of materials. Placement is influenced by terrain, sunlight exposure, and proximity to resources such as ice or regolith. Proper layout reduces the risk of damage from dust, micrometeorites, or thermal effects while supporting efficient operations. Energy and environmental management are integral to the design of the moon base. Solar power is positioned to capture maximum sunlight with storage systems for extended night periods. Thermal systems regulate temperature both inside habitats and in connected infrastructure. Life support systems monitor and adjust air, water, and humidity. Redundant systems ensure continued operation, allowing human activity to proceed safely even if individual components fail. Continuous monitoring and automated control help maintain environmental stability over long duration missions. Incorporating lessons from prior exploration, habitat design balances ease of deployment, protection, and long term sustainability. Inflatable, modular, and underground habitats each provide solutions for initial and expanded operations. Material choice leverages imported metals and in situ regolith. Airlocks, life support, radiation shielding, and thermal insulation are integrated to ensure safe and functional living spaces. Thoughtful design allows human activity to proceed while minimizing risk and maximizing efficiency. The combination of engineering, material science, and environmental adaptation defines the first moon base. Habitat type, structural design, shielding, and integrated systems work together to create an environment capable of supporting humans for extended durations. Every element, from airlocks to insulation, contributes to operational reliability, safety, and long term sustainability. Understanding and addressing the moon's unique challenges is essential to establishing a stable, functional presence on the lunar surface. Choosing a location for the first moon base requires careful analysis of the moon's surface and environment. Polar regions offer distinct advantages compared with equatorial sites. Near the poles, some high points, often called peaks of eternal light, receive nearly continuous sunlight during lunar summer months. This constant sunlight provides a reliable source of solar energy, reducing the need for large energy storage systems. The extended illumination allows solar panels to operate efficiently for most of the lunar day, supporting life support, heating, and equipment operation. Another advantage of polar locations is access to permanently shadowed craters. These craters maintain extremely low temperatures and are known to contain deposits of water ice. Water is critical for life support, drinking, and oxygen production. It can also be split into hydrogen and oxygen for fuel or used to shield habitats from radiation. The combination of near continuous sunlight and nearby ice deposits makes polar sites appealing for long term operations. The ability to extract water in situ reduces dependency on resupply from Earth, improving sustainability and reducing cost. Equatorial sites, on the other hand, offer more moderate terrain for landing and construction. Sunlight cycles at the equator create periods of day and night that last about 14 Earth days each, requiring larger energy storage systems to bridge the long nights. While equatorial locations may have flatter plains for landing and building, they lack nearby ice deposits and require artificial shielding against temperature extremes. Site selection balances energy availability, water resources, terrain stability, and operational requirements. Terrain mapping is a key element in site selection. High resolution topographic maps reveal slopes, crater densities, and surface irregularities. Slope stability affects both construction and mobility. Areas with steep inclines are challenging for landing vehicles and rovers, and regolith movement on slopes can pose hazards for habitat placement. Flat or gently sloping regions reduce the risk of structural stress and make surface operations more efficient. Crater rims, boulders, and uneven surfaces are mapped to identify potential hazards and safe zones for construction and transport. Crater hazards are particularly important. Meteoroid impacts over billions of years have created an uneven landscape with craters of varying size and depth. Large craters can contain boulder fields and loose regolith that impede movement. Small craters may create localized shadows and sharp temperature gradients. Understanding the size, distribution, and orientation of craters allows planners to choose sites with minimal obstacles for landing, excavation, and habitat placement. This reduces risk during construction and operational activity. Surface composition and regolith depth influence site selection. Areas with sufficient regolith provide material for shielding, construction, and radiation protection. Regolith depth affects excavation effort and foundation stability. Sites with loose or shallow soil may require additional preparation or reinforcement before structures can be safely built. Detailed mapping of mineral composition informs the use of in situ resources and helps determine whether local soil is suitable for sintering, 3D printing, or creating protective layers. Sunlight availability must be calculated for both power generation and thermal management. Polar locations benefit from near constant illumination, while equatorial sites experience long periods of darkness. Solar panels must be positioned to capture the maximum light and avoid shadows from terrain features such as crater rims or ridges. Energy storage systems, including batteries or regenerative fuel cells, compensate for periods without sunlight. Efficient placement of solar arrays ensures consistent power supply for life support, thermal control, and operational systems. Access to water ice is mapped using spectral data, neutron detectors, and thermal imaging. Polar craters are particularly promising, with temperatures low enough to preserve ice over billions of years. Ice deposits are often mixed with regolith and may require excavation and processing to be usable. The depth, purity, and distribution of ice influence extraction methods and determine the feasibility of using local water for life, support, fuel production, and radiation shielding. Mapping and analysis of these deposits are essential for long term base sustainability. Communication constraints influence site selection. The moon's rotation and topography create line of sight limitations for direct communication with Earth. Polar sites may experience periods where Earth is blocked by terrain or horizon features. Satellites in lunar orbit provide relay capability, ensuring continuous contact for telemetry, data transfer, and remote control of equipment. Planning the base location includes consideration of orbital paths and satellite coverage to maintain reliable communications at all times. Orbital dynamics also affect navigation and operational planning. Lunar satellites follow predictable trajectories, and understanding these allows planners to schedule communications, energy use, and surface activities. Certain locations may require additional relay satellites or ground stations to maintain full coverage. Positioning habitats to maximize satellite visibility ensures that data from instruments, life support systems, and scientific experiments can be transmitted reliably to Earth. Safety considerations include proximity to potential landing zones for cargo and crew missions. Sites must allow for approach and descent without obstruction. Sufficient flat terrain and stable regolith reduce the risk of landing accidents. Vehicles must have access routes to habitats, power systems, and resource extraction areas. Planning for landing and transport requires careful coordination with terrain maps, slope analysis, and potential obstacles such as boulders or small craters. Thermal stability is part of site evaluation. Areas that experience extreme fluctuations in sunlight exposure, shadows, or reflection from surrounding terrain require additional thermal management. Habitats in regions with consistent illumination benefit from predictable heating and cooling, simplifying design of thermal control systems. Sites near permanently shadowed areas must account for severe cold while balancing access to energy sources and water ice. Dust management is integrated into location planning. Areas with frequent disturbance from micrometeorite impacts or surface operations may produce dust clouds that interfere with equipment. Mapping dust-prone zones helps in arranging habitats, solar arrays, and transport routes to minimize abrasion and contamination. Protective measures include airlocks, dust shields, and designated paths to reduce exposure to regolith particles. In summary, site selection for a moon base involves evaluating sunlight availability, access to ice, terrain stability, crater hazards, and communication constraints. Polar sites offer advantages in continuous sunlight and resource availability, while equatorial regions provide flatter terrain. High resolution mapping of surface features, thermal conditions, and regolith properties informs decisions about habitat placement, power systems, and mobility planning. Strategic planning ensures that the base can operate safely, maintain energy and water supply, and support long term human activity on the lunar surface. Resource utilization on the moon is central to sustainable human presence. Water ice, found in permanently shadowed craters near the poles, provides the foundation for life support, fuel production, and radiation shielding. Extraction methods involve heating the regolith to release water vapor, which is then collected and condensed. Robotic systems or crew operated equipment can excavate ice bearing soil and transport it to processing units. The efficiency of extraction depends on ice concentration, depth, and thermal properties of the surrounding regolith. Understanding these parameters allows for planning of continuous water supply operations. Once extracted, water can be purified for drinking, cooking, and hygiene. It can also be electrolyzed to produce oxygen for breathing and hydrogen for fuel. Oxygen generated in this manner can supplement or replace stored supplies brought from Earth, reducing resupply dependency. Hydrogen and oxygen together provide propellant for spacecraft, enabling local refueling and supporting missions to other destinations. Utilizing local water resources is a key step toward establishing a self sufficient lunar base. Regolith processing is another essential component of resource use. Lunar soil can be transformed into construction materials through sintering, melting, or 3D printing. Sintering involves heating the regolith until it fuses into solid blocks or panels suitable for structural use. Additive manufacturing techniques can build walls, protective berms, or even equipment housing using local material. This approach reduces the need to transport heavy building materials from Earth, lowering launch costs and logistical complexity. Regolith derived materials also provide effective radiation shielding and thermal insulation when properly applied to habitat exteriors. Solar energy harvesting is critical for sustained operations. Solar panels capture sunlight to generate electricity for life support, heating, equipment, and scientific instruments. Placement of panels is informed by detailed mapping of sunlight exposure, especially in polar regions where peaks receive near continuous illumination. Panels are oriented to maximize energy capture while minimizing shadowing from terrain features. Regular cleaning and dust mitigation maintain efficiency, as lunar dust can reduce output by covering panel surfaces. Continuous monitoring ensures that power systems operate reliably over time. Energy storage systems complement solar harvesting. Batteries, regenerative fuel cells, or thermal storage units hold energy for periods when sunlight is unavailable. During the long lunar night at equatorial sites, stored energy supports life support, heating, and operational systems. Thermal storage may involve insulated containers holding heat or phase change materials that release energy gradually. Proper integration of storage and generation ensures that the base remains functional despite fluctuating environmental conditions. Waste management is a critical element of sustainable habitation. Closed loop systems recycle water, air, and nutrients to minimize dependence on resupply. Wastewater is treated and purified for reuse. Carbon dioxide removed from habitat air can be converted into oxygen using chemical scrubbers or electrolysis systems. Organic waste can be processed to recover water and nutrients for potential plant growth or further chemical recycling. The objective is to maintain a continuous supply of essential resources while reducing the accumulation of hazardous or unusable material. Closed loop life support systems integrate water, air, and thermal management. Oxygen levels are maintained through both stored supplies and in situ production from water, electrolysis. Carbon dioxide is scrubbed and either stored or processed for oxygen recovery. Temperature and humidity are controlled to simulate conditions suitable for human habitation, with feedback from sensors to adjust heating, cooling, or ventilation. By closing the loop on essential resources, the base can support long duration missions without immediate resupply from Earth. Thermal management interacts with resource utilization. Energy collected from solar panels can be stored and distributed to regulate habitat temperature. Surplus energy may power heaters for regolith processing units or electrolysis systems. Managing energy and thermal flows efficiently reduces stress on storage systems and ensures that critical operations, such as water extraction and life support, continue uninterrupted. The interplay of power generation, storage, and utilization is essential for maintaining a functional base environment. Local resource planning also includes identifying regolith composition suitable for multiple uses. Some areas provide higher concentrations of silicates or metals, which can be used in construction, manufacturing, or shielding. Mapping these deposits allows planners to position habitats, workshops, and processing facilities near abundant materials. Transport of regolith is simplified by proximity, reducing energy expenditure and increasing operational efficiency. Water ice deposits vary in depth and purity. Some are mixed with fine dust or rocky material, requiring processing before use. Heating regolith releases water vapor, which is captured, condensed, and stored. Systems must operate efficiently under low gravity and temperature extremes. Insulating extraction units and maintaining pressure control prevent loss of water vapor and ensure a steady supply for life support and propellant production. Solar energy infrastructure requires durability. Panels must resist abrasive dust, thermal expansion, and occasional micrometeorite impacts. Supporting structures are designed for low gravity while providing stability during sudden mechanical loads. Cables and conduits connect arrays to batteries or power distribution units, ensuring energy reaches critical systems without loss. Ongoing maintenance, including cleaning and adjustment, sustains performance over long periods. Resource extraction, energy management, and life support are interconnected. Water is essential for oxygen production, thermal regulation, and waste recycling. Regolith provides construction material, shielding, and insulation. Energy drives extraction, processing, and habitat systems. Waste management recycles resources back into usable form, maintaining efficiency. Integration of these systems allows the base to operate continuously with minimal external support. Operational scheduling optimizes resource use. Activities such as excavation, energy collection, and water processing are timed to match solar availability, crew presence, and equipment readiness. Automated systems handle repetitive tasks such as pumping water or circulating air, while human oversight ensures problem solving and adjustments. This combination of automation and supervision maintains a reliable flow of essential resources. Water ice and regolith are used for radiation protection. Ice can be stored in walls or tanks to absorb high energy particles. Regolith applied as surface layers over habitats or tunnels reduces radiation exposure. Thickness and density of protective material are calculated based on radiation measurements from prior missions. Proper application ensures that inhabitants receive acceptable levels of exposure while allowing construction to proceed efficiently. Energy storage and distribution systems are sized according to operational demand. Life support requires continuous power, while processing units for water and regolith are flexible. Batteries store surplus energy during peak sunlight, releasing it during periods of low input. Thermal energy may be converted into electricity or used directly to maintain habitat temperatures. The integrated system ensures continuous operation and minimizes risk of failure. Waste recycling contributes to resource sustainability. Water recovery systems capture moisture from air, condensate, and wastewater. Nutrients from organic matter can be processed for plant growth or chemical reuse. Carbon dioxide removal allows oxygen regeneration. Each loop reduces dependency on resupply and maintains a closed system. Redundant units ensure that failures in one subsystem do not compromise overall functionality. Sustainability planning extends to mobility and construction operations. Excavators, rovers, and robotic arms are powered by stored energy and solar arrays. Regolith transport for shielding or building uses predictable paths to reduce dust interference and mechanical wear. Maintenance of equipment is integrated into schedules to prevent downtime. Resource efficiency is central to long term habitation. Resource utilization is planned to support incremental expansion. Initial habitats rely on limited extraction and storage, gradually incorporating additional ice and regolith processing as more units arrive. Energy systems scale with habitat growth, and life support loops adapt to increased occupancy. This phased approach ensures that the base remains sustainable as the population and operational complexity increase. In summary, the first moon base will depend on effective use of local resources to maintain life support, construction, and energy systems. Water ice provides drinking water, oxygen, and fuel. Regolith supplies building materials and shielding. Solar energy is harvested and stored to power operations. Closed loop waste management reduces dependence on resupply. Integration of these systems creates a functional, sustainable environment, allowing humans to live and work on the moon for extended periods while minimizing reliance on Earth. Transporting materials and personnel to the moon requires careful planning of launch windows and travel time. The moon completes an orbit around Earth every 27.3 days, creating periods when energy efficient transfer trajectories, called Hohmann transfers, are possible. Launches are scheduled to match these windows, minimizing fuel consumption and allowing precise arrival at lunar orbit. Travel time for these transfers is typically 3 to 4 days, depending on trajectory, spacecraft speed, and orbital insertion. Payload constraints determine the size, mass, and volume of cargo that can be delivered in each mission. Every kilogram must be carefully accounted for, balancing fuel, life support, construction materials, and scientific equipment. Cargo delivery systems include both landers and orbiters. Landers transport supplies from lunar orbit to the surface. These vehicles are designed to decelerate safely, accommodate uneven terrain, and distribute weight evenly to prevent sinking into regolith. They carry modular habitats, construction equipment, rovers, and fuel for local operations. Orbiters provide staging for supplies and relay communications. Some orbiters also store additional cargo for later descent or provide temporary storage for resources collected from the surface. The combination of landers and orbiters allows sequential delivery of large and diverse payloads while maintaining operational flexibility. Mobility vehicles on the lunar surface extend the operational range of crews and robotic systems. Lunar rovers transport personnel, equipment, and collected samples across plains, cratered areas, and slopes. Rovers are designed for low-gravity, uneven terrain and abrasive dust. Wheels, suspension, and power systems are optimized for both traction and durability. Some vehicles are pressurized, allowing crews to travel without spacesuits for short durations, while others are unpressurized and transport cargo or robotic units. Their use enhances productivity, enabling crews to access resources, perform construction, and conduct scientific studies across wider regions. Robotic precursors play a critical role in base preparation. Autonomous rovers, excavators, and manipulators perform tasks ahead of crew arrival, such as clearing terrain, deploying initial infrastructure, and collecting data on regolith terrain stability, and ice deposits. These robots reduce risk to human crews and allow habitats and power systems to be installed efficiently. Teleoperation from Earth or orbital satellites can guide robotic operations, ensuring precision and adaptability. Robots can also inspect the landing zones and prepared surfaces, verifying safety for incoming landers and personnel. Autonomous construction uses robots to assemble modules, process regolith, and create shielding. Techniques include additive manufacturing, where machines 3D print walls, berms, or other structures using local materials. Excavators prepare foundations or tunnels. Surface manipulation equipment moves regolith to cover habitats or reinforce structural components. Automation reduces human labor, minimizes exposure to hazardous environments, and ensures that critical infrastructure is in place before long duration crews arrive. Coordination between robots, habitat modules, and energy systems allows construction to proceed with efficiency and safety. Launch and resupply planning must consider timing, payload capacity, and mission priorities. Regular cargo missions bring consumables, replacement parts, scientific instruments, and additional habitat modules. Payload constraints require optimization of packaging, mass distribution, and volume allocation. Supplies are staged in orbit or on the surface for sequential use. Advanced planning ensures that critical resources, such as water, oxygen, fuel, and energy storage units, arrive when needed to maintain continuous operations. Emergency return systems are integrated into logistics planning. Crewed missions have contingency spacecraft capable of returning astronauts to Earth in case of system failure, medical emergency, or environmental hazard. These vehicles are maintained on standby in lunar orbit or at the base, with fuel and life support sufficient for immediate departure. Emergency protocols also include resupply of critical consumables, temporary habitat redundancy, and power support to ensure crew survival until evacuation or repair is possible. Surface transport routes are carefully designed to connect habitats, resource extraction sites, and landing zones. Paths account for terrain gradients, regolith depth, crater fields, and boulder distribution. Regular use of these routes reduces dust disruption to other areas and prevents wear on rover wheels and structural surfaces. Signage, beacons, and GPS-like navigation aids adapted for the lunar environment support safe, reliable mobility. Mobility planning also incorporates potential hazards from micrometeorite impacts and sudden slope shifts. Payload management considers both mass and volume. Habitat modules, water and fuel tanks, scientific instruments, and power systems each require careful placement within landers. Distributing weight evenly prevents tipping or structural failure during descent and landing. Equipment is secured against vibration, impact, and movement caused by acceleration and low gravity. Modular designs allow flexibility in cargo arrangement while maximizing space usage. Energy for logistics operations is integrated with surface infrastructure. Vehicles may rely on battery packs charged from solar arrays or regenerative fuel cells. Mobile units support excavation, transport, and construction operations without drawing excessive power from stationary systems. Energy allocation ensures that essential life support and habitat systems remain operational during simultaneous cargo delivery and surface mobility activities. Training for crewed logistics is informed by previous robotic and human missions. Procedures for loading, unloading, operating rovers, and assembling modules are standardized. Automation and remote supervision reduce human error. Redundant systems and pre-planned contingencies ensure that the base can continue operations even if one logistic path is disrupted. Safety, efficiency, and reliability are central to mission planning. Coordination between orbital and surface operations maintains operational continuity. Orbiters track landers and crewed vehicles, relay commands, and monitor progress. Surface sensors and telemetry provide real time feedback on terrain conditions, vehicle status, and environmental factors. This integration allows precise navigation, scheduling of surface operations, and timely response to hazards or delays. Construction logistics involves staging equipment in sequence to optimize workflow. Excavation tools, its regolith processing units, and habitat modules are delivered in an order that allows immediate use upon arrival. Robots prepare sites while humans perform assembly and system integration. Coordination reduces idle time, minimizes exposure to hazards, and ensures that energy and water resources are applied efficiently. Long term logistics planning accounts for population growth and base expansion. Additional habitats, laboratories, energy systems, and mobility units arrive over time. Pre planned delivery schedules and adaptable transport methods allow the base to scale operations without disruption. Planning considers storage, redundancy, and operational flexibility to accommodate increasing resource demands. Integration of all transportation systems ensures continuity of supply and operational effectiveness. Launch timing, orbital insertion, landing procedures, surface mobility, and robotic operations are coordinated to maintain flow of materials and personnel. Redundant pathways and emergency systems ensure that the base remains functional under all foreseeable conditions. Resource delivery, infrastructure assembly, and crew movements proceed smoothly, supporting the sustainability and reliability of the lunar base. In summary, logistics and transportation on the moon encompass precise launch windows, travel trajectories, and payload management. Landers, orbiters, rovers, and robotic systems ensure safe delivery, mobility, and construction. Autonomous operations prepare the site and maintain infrastructure. Emergency return and resupply protocols provide safety and redundancy. Efficient coordination of these elements enables the first moon base to operate continuously, support human activity, and expand sustainably across the lunar surface. The long term prospects of a moon base include extensive opportunities for scientific research. Habitats provide platforms for experiments in low gravity, vacuum conditions, and radiation exposure. Laboratories on the surface can study lunar geology in situ, examine regolith properties, and analyze mineral composition. Instruments placed around the base monitor seismic activity, track micrometeorite impacts, and record temperature and radiation patterns over time. Observatories on the moon can take advantage of the lack of atmosphere to observe the sun, stars, and distant galaxies with unprecedented clarity. Observation platforms placed on elevated terrain or in orbit complement surface based research. Telescopes benefit from stable, dry conditions and minimal light pollution. Arrays of sensors can monitor cosmic rays, solar wind, and space weather events, providing valuable data for both lunar operations and Earth based scientific studies. Continuous data collection allows long term studies of radiation effects on materials, electronics, and human physiology. Research facilities are designed to expand as more infrastructure becomes available, allowing increasing complexity of experiments and monitoring systems. Expansion of habitats is planned in a modular and scalable manner. Additional modules are delivered as new technologies become available and operational requirements increase. Living quarters, laboratories, storage areas, and workshops are connected through pressurized corridors and tunnels. Expansion follows site planning principles that consider terrain, solar illumination, energy supply, and access to resources such as ice and regolith. Phased growth allows the base to support larger crews and more diverse activities while maintaining operational safety and environmental control. Long term human presence involves rotation of crews, resupply missions, and infrastructure upgrades. Habitats are designed for durability, with maintenance systems for air, water, and energy that reduce reliance on external support. Life support systems are upgraded as new technologies improve efficiency. Storage for consumables and spare parts ensures continuity of operations during temporary gaps in resupply. Planning considers not only daily operations, but also potential decades long occupancy, allowing gradual buildup of permanent infrastructure and scientific facilities. Collaboration between international space agencies and private companies enhances the scale and efficiency of lunar operations. Agencies contribute expertise in mission planning, life support, and scientific instrumentation. Private companies provide launch capability, habitat development, logistics solutions, as in advanced robotics. Partnerships allow shared resources, joint research projects, and coordinated delivery of equipment. Cooperative efforts reduce duplication, maximize efficiency, and expand the scope of exploration beyond what any single entity could achieve independently. Coordination of research and industrial objectives is central to long term planning. Scientific investigations often rely on infrastructure also used for construction, resource extraction, or energy production. Laboratories benefit from power systems designed for mining operations, while extraction equipment gains access to transport networks originally intended for research payloads. Integrating scientific, operational, and industrial goals ensures that the base evolves efficiently and sustainably, with each new system supporting multiple functions. Potential for industrial and mining operations grows as resource utilization capabilities expand. Regolith processing, water extraction, and in situ production of fuel and construction materials form the foundation for industrial activity. Metals and rare elements in lunar soil may be extracted for use on the moon or eventual shipment to Earth. Automated machinery and robotic systems allow large scale operations without continuous human oversight. The combination of scientific observation, industrial production, and habitation infrastructure creates a self reinforcing ecosystem for long term presence. Energy infrastructure expands alongside habitation and industrial systems. Solar arrays and storage units are added as new habitats and processing facilities come online. Energy management systems distribute power efficiently between life support, scientific experiments, excavation equipment, and mobility units. Redundancy and flexibility ensure that new modules can be integrated without disruption. Future energy systems may incorporate advanced solar technology, regenerative fuel cells, or small nuclear units, increasing operational capacity and reliability. Transportation networks extend as the base grows. Rovers, cargo vehicles, and robotic systems provide mobility for crew, supplies, and industrial equipment. Surface pathways are maintained for safety and efficiency, connecting habitats, laboratories, extraction sites, and landing zones. Orbital relays and communication satellites scale with the expansion of infrastructure, ensuring continuous command, telemetry, and data flow. Logistics systems are designed for both routine supply and emergency scenarios. Scientific research continues to drive expansion priorities. Studies of lunar regolith, ice deposits, and geology inform site planning for additional habitats, energy infrastructure, and industrial facilities. Continuous monitoring of environmental conditions guides construction, resource extraction, and safety measures. Long term observations of space weather, cosmic rays, and micrometeorite impacts help refine habitat shielding and operational protocols. Data collected over years supports both the immediate needs of the base and broader scientific objectives. Habitat expansion includes specialized facilities. Laboratories for biology, chemistry, and materials science provide controlled environments for experiments. Storage modules maintain essential supplies, while workshops enable repair and fabrication of equipment. Communication centers manage both surface and orbital traffic. Infrastructure is designed to be adaptable, allowing modules to be repurposed or upgraded as technology advances and mission priorities evolve. Crew rotation and habitation planning are optimized for efficiency and safety. Schedules account for workload, maintenance, and scientific activity. Life support systems are scaled to match crew numbers. Redundancy in oxygen, water, and energy supply ensures that critical resources are maintained during transitions. Rotation protocols also provide experience in long duration operations, building knowledge for future expansion and sustained occupation. Industrial activities, such as regolith processing and fuel production, are coordinated with scientific and habitation requirements. Extraction sites are mapped for efficiency and safety. Material transport systems connect these sites with construction areas and storage units. Automation reduces the need for constant human involvement and ensures continuous operation. Industrial infrastructure expands in parallel with habitats, maintaining a balance between human presence and resource utilization. International and commercial collaboration continues to influence expansion strategy. Shared knowledge, joint missions, and pooled resources allow rapid deployment of new modules, equipment, and research systems. Standardized interfaces and modular designs enable interoperability between different organizations' hardware. Cooperation ensures that scientific, operational, and industrial goals are aligned, supporting efficient growth of the lunar base. Communication and data networks expand with new facilities. Surface relays, orbiters, and long range antennas provide reliable links for operational control, scientific data transfer, and coordination with Earth. As the base grows, redundancy ensures uninterrupted communication. Networks are designed to integrate new habitats, laboratories, and industrial units without disruption, allowing continuous data flow for both research and operational purposes. Long-term expansion. Planning incorporates environmental and logistical considerations. Solar exposure, terrain stability, regolith composition, and access to ice guide placement of new structures. Logistics networks, energy systems, and mobility pathways are scaled to support increased crew and equipment. Continuous monitoring and analysis allow planners to anticipate challenges and adapt infrastructure to maintain safety, functionality, and sustainability. The integration of science, habitation, energy, industrial activity, and logistics forms a cohesive framework for the future moon base. Each element supports others. Energy powers laboratories and extraction units. Processed regolith provides shielding and construction material. Water supplies support both life support and fuel production. And transport systems connect to all infrastructure components. Expansion is coordinated to maintain efficiency, safety, and long-term sustainability. In summary, the moon base's future includes extensive scientific research, modular habitat growth, and long-term human occupation. Collaboration between space agencies and private companies accelerates infrastructure deployment and operational capabilities. Industrial operations and resource utilization support expansion while minimizing reliance on Earth. The integration of habitation, science, energy, and logistics creates a foundation for sustainable lunar presence capable of continuous research, exploration, and development.